And now the universal holomorphic algebra is an associative algebra. In which you can give the basis. Here I can give it in a very simple way. If it's an associative algebra, this means that I can not only take these products, but I can also take the products, the products between the elements themselves. So this means that I can say what is x plus 2 degree k. I can say what is x. I can say what is h 2 degree l, and I can say what is x minus 2 degree m. This is just, of course, the multiplication taken k times, here l times, and m times. And there are certainly some coefficients. So this forms the basis. These polynomials form the basis. And in fact, the numbers k, so k is equal to 0, 1, etc. L is equal to 0, 1, etc. And m is equal to 0, 1, etc. I can denote this basis, say, by BKLM. And what happens if I put 0, 0, 0? So the convention is that any generator in 0 degree is the unit element, which is there. This is also here for those. So B00 is the unit element. So in a sense, this basis incorporates the unit element. Okay, and now the point about quantum groups is that of course this algebra, the universal holomorphic algebra, is also a Hopf algebra, but it has but the structure of the Hopf algebra is in a sense trivial. It means that, for instance, delta of z will be equal to 1 times z plus z times 1 for all generators. So for z equal h, x plus minus. Gamma of z will be equal to minus z. Epsilon. The only non-trivial point is about the epsilon. The epsilon of h. 1 second. No, of course, it's also trivial. So the epsilon of everybody of this is also trivial, and the only non-trivial is, of course, epsilon of 1. Okay, so this is trivial, but we can make a Hopf algebra, a non-trivial one, and even obtain a quantum group if we modify these relations. In fact, we modify only one relation. We modify this relation, and we modify it in the following way. We say that we modify the bracket h plus x minus is now equal to, now I'll write something that is maybe not well defined by itself, but we have to live with it. Now, so what is, so Q initially is some abstract entity. We can think it is a number. Of course, then this can be, of course, written Q h over 2 if it is a number. It can be written as I exponent of h over 2 logarithm of q. Of course, then of course you may say, yes, but this is an exponent of a generator, maybe it is convergent, maybe not. For instance, this is considered as a formal equality, although one would use also it informally. Now it depends what is Q. And Q can be, if it's a complex number, for instance, we can put that Q would be equal to Q over H. And then this, what I have written here, will pass to hyperbolic sine of H, of H times small h over 2 over hyperbolic sine of H over 2. This is useful, for instance, if H is real. Sometimes it is good to have Q to be a number on the unit circle. In that case, we write Q as E 2 pi I tau. In that case, so this is in this case, and in that case, this will be normal sinus of P tau H over sine P tau, sine P tau. Now, for those of you which are more mathematically oriented, there is the so-called H-adic topology. H-adic topology. And then we have F, such notation. This is the ring, a formal power series. In H over a number field F. And there's some details. There are some details which, of course, I'm not going to enter. But there are some more rigorous treatment. And in fact, it is given in the book of Charlie and Presley. If you're interested, you can look this in this book.
Formal series means we don't care the covariance.
Yes, yes. It means that this is just we write with formal coefficients, and we don't ask anything about the convergence. In a sense, if H is an operator takes an eigenvalue, then of course the eigenvalue is some number, and then these things make sense. So anytime you substitute H with eigenvalues of H, then these relations make sense. The only problem is, in a sense, about the formal justification. And also because it's an operator, sometimes you want to work abstractly and not only with the eigenvalues. So that's why sometimes it is necessary to know this thing. So I should mention that similar things were also done in the case of supersymmetry, in the case of affine Kac-Moody algebras, and so on. But what I should not forget to mention, which is important, is that in replacing this operation by this operation, we actually didn't change the basis. This basis remains the same. So it remains only the operations. Well, why this operation is important? You see, I said this is a basis, but what I mean? Suppose I multiply here with H, but then it has to be here, it has to be in the middle. But using the commutation relations, I can bring it in the middle.